All right, so we're going to go through this practice test rather quickly here. Let's go ahead and start with the phosphate ion. Phosphate is PO4 minus, and it asks for the hybridization around the phosphorus. Well, first it helps to know that that the phosphate ion has a 3 minus charge. A 3 minus charge tells you that the total of all the formal charges must add up to equal a -3. So let's go ahead and start by drawing the Lewis structure. We've got a phosphorus and 4 oxygens, but again we want 3 of them to have a -1 charge because they should probably come from the oxygens, because the oxygens are the most electronegative thing. The negative formal charge should fall on the most electronegative thing, and one of them is probably going to be neutral. Something with a 0 formal charge like this oxygen can be determined based on the periodic table. So if you look at the periodic table, you can tell that oxygen needs two bonds in order to make it a 0 formal charge. Whereas these guys, if you do a single bond, this would have a -1 formal charge, because valence minus 6 minus dots would be 6 minus 1 minus 6, which would equal -1. So all of these oxygens, if you put the appropriate amount of electrons around them, would have a -1 formal charge. And then the phosphorus would be 0, because 5 minus 0 is that. So is 0. All right, so it says, what is the hybridization about the phosphorus? Well, if you remember hybridization, it goes in this order. It's an S, then 3 Ps, then 5 Ds. So looking at it, there's 1, 2, 3, 4 electron groups around the phosphorus. So we just go 1, 2, 3, 4, count 4 over. That's sp3, so our answer over here would be sp3. Number 2, it says, what is the bond order? Well, here we have 4 things and they're not created equally. This structure will resonate. So this bond right here will be shared between all of these. So it's going to be moving around. Now there's a couple ways you can think about it, but for the most part, essentially we have 5 total bonds divided among 4 things. The 5 total bonds coming from 1, 2, 3, 4, 5, telling you each one gets 1 1/4, or the answer of C. All right, number 3, how many total resonance structures can be drawn for phosphate? Well, if we take this phosphate right now as it is, and I'm not going to draw the outer electrons right now, instead we're just going to do this. This is going to move around. This can be, the double bond can move here. The double bond can move over here. The double bond can move over here. And then we can even have a structure that might look like this. And this would be a fairly unstable structure. But this says, make sure you keep in mind that less stable structures may be possible, hint, hint. So looking at this one, all of these would have a -1 formal charge, and this would be a +1 now. And that's still a reasonable thing. Anytime you have a -1 and a +1, you want to make sure you create a bond there. So it's not necessarily a stable structure. These 1, 2, 3, 4 are the most stable, but this is a potential impossible structure, and therefore your answer would be C5. All right, another question. What is the molecular geometry about the second carbon in 2-pentyne? Well, 2-pentyne would be 5 carbons. Pent tells you there's 5. The "-ine" tells you that it's a triple bond. And the 2 tells you where the triple bond is. So here we have 1, 2, 3, 4, 5. And the triple bond will lie on the second. If you label these 1, 2, 3, 4, 5, it'll lie on the second carbon. So we'll put the triple bond there. Now we just fill in the rest with hydrogens, ensuring that each carbon has 4 hydrogen bonds to it. Oh, shouldn't put it there because there's a carbon with 1 and then 3 right there. All right, so it wants to know about the molecular geometry around this thing. Well, here we have 1 bond here and a triple bond here. That makes sense because carbon should have 4 total bonds. And if you look at it, there's nothing else on there. there should be nothing else on there. And because of that, it only has 2 electron groups. 2 electron groups would be 180 degrees or linear. So the answer is actually D, none of these. The next question, rank these in terms of increasing lattice strength or energy. Talks about magnesium oxide, sodium oxide, and aluminum oxide. Now, if you remember, there's 2 things that affect the lattice energy: size and charge. So as size increases, the energy decreases. Oh, I need a new pen. Okay. As size increases, the energy is going to decrease between the things, but as charge increases, the energy will increase. So size and energy are inversely proportional, but charge and energy are directly proportional. So when we look at this, we have sodium, magnesium, and aluminum are the only things that we're comparing. Now, if you remember in class, charge trumps size. Charge is more important. So if charge is more important when we're looking at this, we have to think about the charges of each of these. Oxide is the same in all cases, that's a -2. But sodium is a +1, magnesium is a +2, and aluminum is a +3. So again, as charge increases, the energy must increase. So here we have aluminum, magnesium, and sodium, and the energy must increase as the charge increases. So when we go over here, the only potential answer is B. And in fact, if you look at it, aluminum, if you look it up, aluminum actually has something like 15 megajoules it takes to break this, where these guys are in the kilojoule range. So aluminum oxide is an incredibly strong lattice, very hard to break and turn them into gaseous ions. All right, number 5. Actually, let's take a break.